Hello all. In this particular video, we are going to continue our discussion on the relationship or modeling of RDFS language constructs with logic. And basically, in this particular part, we'll be talking about how we can use first order logic family to model the different constructs in RDFS, right? To start with, we know that we need to define the predicates and the functions, all those stuffs we know in first order logic, and we'll be using those to kind of define different constructs in RDFS, right? Now, let us try to start with the example of how to model the lists, right? So the lists, you know that they are closed containers. So this list is a closed container in RDFS, right? Now, what do they contain? They contain the elements, but this is a closed thing, right? And this list is always having a first element, and the rest of the elements are called the rest, right? Now, finally, we will end up at certain point of time of the processing the list, which will be the nil, RDF nil, right? Now, how do we represent the empty list? Basically, we'll be representing that with a constant, which is nil, and you know that is a constant in first order logic, right? How do you say that there is a first element in L? So we'll be using a function to represent that first order logic function to say that something that is equal to the first element of the list. Similarly, we can say that there is something that is equal to the rest of the list, and it will be modeled as a function also. How do you say that an item occurs in the list or is a member of the list? Basically, we say that item x list xl, which is basically a predicate. And finally, how to test that a given object L is a list or not. So basically, you have a predicate. We'll say that that whether L is a list or not, right? In RDF or RDFS, we know that we can define classes, and we can say that a particular resource is a member of that class or not, right? For that, we use something called RDF type, right? So by this, we assign membership of something, some resource into a class, right? So for that, we need to have predicate that will do this, right? Now, before going to explain this, let us think about a very generic RDF statement, right? So what is a very generic RDF statement? You have basically three things: S, P, and O, right? Now, how we can model this? So basically, you can draw this S, P, O like this, right? So we can take this P to be the predicate name of the first order logic predicate. So from now on, I'll be calling this P to be, say, a property, right? Because we'll be using the name predicate to represent a predicate in first order logic. Otherwise, the things will be confusing, right? So this property is converted into the predicate name, right? And then you can take this to be the first argument and take this O to become the second argument, right? So now take this kind of statement which says that subclass of is RDF type property. So you can see that we are not using the prefixes in many places. So that we will do, assuming that you understand the what would be the prefixes, right? By following this logic, so we can take this here, say type. We can take this part here, subclass of, and take this part here to put it as property, right? You can see that we have got this, right? Also, we can represent this SPO or say SPO in a form like prop val PRV. So it is something like, if we take this SPO, it will be prop val this PSO. Basically, R is equal to say S and V is equal to O. Now you can see that I have a triple. I can represent the triple in this form. I can represent the triple in this form also. So which one we should choose, right? Now you see, this type is a very specific thing which is defined in the vocabulary of RDF. So for that, we can basically use this structure by saying that subclass of is a type of property. But you think of any triple where, say for example, say Indian cricket team has member, say has member, say MSD, right? Now there are two modeling ways. So we can convert this into a first order logic predicate form like HM, ICT, MSD, or I can say prop val property is say HM, then ICT, then MSD, right? Now which one to choose? We will go for this because of the very fact, when we are using this kind of properties which can be defined by the community, by the user in general. So for that, it is not good that you have predicates like this, where the name or the predicate head can be anything, right? So that will add many predicates in your system which you don't want to have, right? Instead of that, if you take this kind of approach, you can see that this predicate name is becoming an argument to a very generic predicate, or this property name is becoming to be the argument of a very generic predicate, which is prop val. Now you have got only one predicate type like prop val, and with that you can represent any statement concerning any property or any subject and any object. So that's why when we talk about the very generic or very user defined properties or triples, we'll be using prop val. But when we have something like say RDF type, instead of using prop val, so if you convert this this particular relation, this particular triple into this prop val form, how would it look like? It will look like prop val type, because this type is your property. What is the subject? Subclass of. And what is the object? Object is a property, right? So you can see that we can also write this particular statement in this form, right? Now we can use this, but it is not really necessary, because I know that type is a kind of vocabulary that is defined and well understood by the community, and we don't need to put that as an argument in the prop val predicate. So we can treat that specially, because this is a special vocabulary, right? So whenever we have something like this RDF RT, that means R is a type of T, then that is equivalent to the predicate that is prop val type RT, right? So for a standard vocabulary like type, we'll be using this kind of short form, but for others we will be using this prop val, right? So we can represent any RDF triple with this PRV, and we can assert any instance and relationship between an instance to its class. Basically, something is an instance of another thing by this type predicates. Like here I'm saying that class is an instance of the class. Resource class is an instance of the RDFS class. The RDF property is an instance of RDFS class. RDFS literal is an instance of RDFS class, right? So this is how we can represent this statement, this axiomatic statement using the type predicate, right? Now, how do we define everything is a resource, right? So what do we mean by everything? This everything can be property, can be class, or can be literal. So we are just doing this for class and properties, and you can extend that to the literals also. So this is what we are saying, that if something is P is of type property, then we can infer that this P is of type resource, right? And if C is of type class, we can also infer that C is of type resource, right? So because of the very fact that this is the class of resource and this set of properties, this is a subclass of R, and set of classes, they are subclass of resources, right? So these are the set of classes, right? Now the predicate in RDF statement, so I'll refresh it. So it is basically the property in an RDF triple. It must be a property, right? It will be a type of property. How do we write that? So basically we can say that we have something like prop val p rv, which is basically the uh, the first order logic representation of an RDF triple, right? And the RDF triple will be R P V. If you have something like this, you can say that P is of type property, right? Now, how do you say that RDF type is a property? Basically, you say that type of type is property, right? So basically, this is representing this triple. RDF type is RDF type RDF property, right? Now, how do you model that domain of type is resource and range of type is class, right? So, what you have in type, say for example, I can say that Hardik Pandya, which is an instance or resource, is RDF type, say all-rounder, right? What is this? This is a resource. What is this? This is a class, right? So the domain of type is resource and a range of type is class. So how do we write this in first order logic form? So if we see something like this, say R is of type C, then we can say that type of R is resource and the type of C is class, right? That is how we can represent the thing. There is something called functional property, which we have not discussed earlier. This functional property, which I have written in a short form like FuncProp, this property, whenever you assert something, some property to be a functional property, that means that that indicates uniqueness of something. So this functional property relates to uniqueness of something. Let us take an example. Let's say you have a person P1, right, who is a resource, and say DOB, date of birth. So you have a date, right? Now let's say I have another thing, say DOB, this, right? This cannot be true. Like a person can have only one date of birth, right? So if you can impose that kind of rest, so that means you cannot have more than one outgoing edge from this resource having this label DOB property, right? You cannot have more than one outgoing edge which is labeled with this property which has been defined as the functional property, right? So you see that this date of birth is unique to a person, and whenever we try to model something like this, we declare this property to be a functional property. Now how do you represent the fact that a particular property is of type functional property? First of all, this P should be of type property. You cannot say define a class to be functional property, right? And then you need to assert the fact that uh, mm, the uniqueness fact, right? And how do you do that? Let us assume that you have a resource R and a value V1 and a value V2, right? For that, you have the prop val, so P R V1. So this tells you that a particular resource R has got value V1 for property P. So let me draw it. So you have say P R who has got a value for P is V1, right? And prop val P R V2. It has got another outgoing edge V2, right? And you know that that is not possible, right? That you should not allow. And how do you do that? We have done many of these kind of examples while we modeled uniqueness or more than two or at least two brothers. So we have done all those sort of thing in first order logic. We will be doing the same trick here, right? What will be the trick? If this is true, if we assume this to be true, then we say V1 is equal to V2. So you merge these two together. So you merge these two together. So this will be your representation of something of having type functional property, right? Now come to this Reified statement. Let us try to recapitulate the structure of a Reified statement, right? What was the structure of the Reified statement? So you have something, say this has got some certain property, this, and this is having a subject, this is having a predicate, and this is having an object. So these are relations, these are properties, sub, pred, and obj, and this were having some values, and this is of type statement, right? So one example, again I can say one example of this. For example, Sherlock Holmes suspects that the gardener killed the butler, right? Now let us see how to model the Reified statement, right? So you can say that if something is of type statement, then that is also is a type of resource. Anything is a resource. So you can tell it for anything that you have semantic there, right? Or in RDFS or RDF, right? Now you can see that statement is a type of class. So the statement, as it is having an incoming edge having the level type, so that means the class. Something is an instance of this, and if that is so, this is a class, right? This is true. Now this RDF Reified statement, they can be decomposed into three parts, right? So RDF statement has got three parts: the subject, predicate, and object. So how do we model that? So we say that something is of type RDF statement if this is so, then this becomes true. So prop val this there will be something called predicate, and this statement. So let us draw it once again. So this is your ST, right? This is your instance of a statement. This is your subject. This is the predicate. And this is the object property, right? So I can take this part first. So I am taking this part. Maybe you can take the subject part. Let us go one by one. Say subject, and what is the resource? The resource is ST. What would be the value? The value you can take anything, right? Say for example R, right? And let us focus on this predicate. Prop val predicate, then ST, and here you will be having some values. So for example, this is your gardener, this will be your, say, butler, right? So here you will be having the predicate. Let us name that to be P, right? And prop val object ST, you can name it anything like say value, right? And there should be at least one subject. Sorry, you have used R, right? So you have used R, there exists P, and there exists V, right? So the subject has got at least, sorry, a statement has got at least one subject, one predicate, and one object, and that's how we can model in first order logic, right? Now how do you model that every statement has exactly one subject, one predicate, and one object? How can we do that? We have discussed this already, right? So how do you ensure that a particular value for a given subject and predicate is unique? So you can use functional property. You can say that subject is a functional property, predicate is a functional property, and object is a functional property. So you just say type subject FuncProp, type predicate FuncProp, and type object to be the FuncProp. Right? Now we can also say that if for a given Reified statement, if we have something like this, that subject of the statement is R, we can say that this ST, or if you have something like this ST is a type statement, and R is of type what? resource, right? And here what you can say, V is of type statement, ST is of type statement, and P is of type property. ST again is of type statement, and V is of type, you can say it can be a resource or it can be a value also, right? Let us try to model this in first order logic. Very simply you can do that. So I can say type of ST is statement, right? And type of R is resource, right? What we can write here? We can say the type of ST is statement and type of say P is property. Here we can say that the type of ST is statement and type of say V is a resource or type, let me write it in the next line, type of V is say literal, because they can be values also, right? And you have to have an or relationship between them, either a resource or a literal, but not both, right? And what you can do, you can write a bracket, put parenthesis before and after this expression, right? So this is how we can represent the typing information for different elements in a Reified statement, right? Now let us focus on the containers, right? Now the containers, they are resources, right? Everything is a resource. I can say the type C, if C is a type of container, C is also a type of resource, right? How do you model that containers are bags, sequences, alternatives, or lists? You can simply say that type of C is bag or type of C is sequence or type of C is alt or type of C is list, right? Now, how do you model something like bags and sequences are disjoint, right? So you can say that it is not the case a particular thing that will be of type bag and that will be of type sequence at the same time. So it is not the case that a particular thing will be an instance of bag, also instance of sequence, right? So basically this bag is a set, you can represent this bag is a set, and the sequence, all the sequences you can have, they are also sets and they are disjoint. So if something is belonging to this, it cannot belong to this, right? So you can also write this particular thing in this form. So for example, if something is of type bag, then it implies that it is not of type say sequence, right? And of course the other way of implication will also be true, right? Now you have got selectors, right? So you have something like which is of type bag, which is of type bag, and it is got say RDF underscore 1 to be this, and RDF underscore n to be this. So you can observe one property that we do not repeat this property level. So they're all unique, right? So that's why you can define all these kind of uh, uh, mm, these relations, they are our properties, they are functional properties, right? And if you have something like this is of type you have something like, so this is the predicate and you have got the container which has got the value. So this is your C, this is your underscore n, and this is your a, right? If this is so, then you can say that the C is a type of container, in this case which is a bag, and you know that the bag is a container, right? Now how do you say that subclass is a property? Simply you say the type of subclass of is property, right? Now how do you model something like this? If C is a subclass of C prime, then all instances of C is also instances of C prime. So here what we are doing exactly. So you have this this is your C prime and this is your C, right? And all the instances that are in that are resources that are instances of C, they are also instances of C prime, right? So this is how we'll be writing. So you want to define this subclass of C is a subclass of C prime, right? So first of all, you need to assure that this C is a type of class and C prime is a type of class, right? And if something is an instance of class C, so that is how we write something that is an instance of class C, that will imply that particular thing X is also an instance of C prime, and this should hold true for every X, right? Now how do you model the next thing? That is this P is a subproperty of P prime if you can infer P prime xy whenever you assume that Pxy is true, right? So you have something like this. Say X is a mother of Y, right? And from this you can infer that X is a parent of Y, right? So this xy, they belong to mother of, and this xy, they belong to parent of relation also. So we say that a property P is a subproperty of P prime. Again you have to say that this P is a type of property, right? And P prime is also a type of property, right? And whenever you have say something like this prop val, what is the first element in prop val? The property name, then resource, then value, right? If you have something like this, then you can also say that prop val P prime RV, right? And it should hold true, for all R and V, right? This should hold true for all R and V, and of course this will hold true with along with the other predicates, right? So this is how we can encode the subproperty of relationship in first order logic. Now we have got constraint resource. What are the constraint resources? Basically, they are the constraint. They hold the constraint properties like domain and range, right? So these constraint resources, they are relevant to domain and range of the properties, right? So similarly, everything that is that you can think of is a resource. You can also define that every constraint resource is a resource, and you can say that this constraint resource is a subclass of a resource, right? Now, how do you define that constraint properties are properties and they are as well as resources? So if something is a constraint property, then that the type of that is a constraint resource, and the type of that particular thing is property, right? So basically you can see that you have something, say, for all CP which we are omitting, right? This is assumed, right? Now we can define something like this, that this domain, which is basically RDFS domain, to be a constraint property, and RDFS range, that is also a constraint property, right? Now how do we represent this? If domain of P is D, then for every Pxy, then X belongs to D also. So what we are trying to model here, so we are saying that we have something like this, X, Y, P, right? And we are saying that domain, so this we have already discussed, but again I am repeating so that the idea is reinforced, right? So P has domain to be D. So in that case, what we say, that X is an instance of D. How do we write that? So this is what we are saying, the domain of P. So this is the E part of it. The domain, which is basically your P in the prop hell. So don't be confused with this P. Let me remove this. So the domain of P is D, right? So if you have something like, say, prop val P x y, so from this what you can infer, you can imply that type of x is D. Basically D, x is an instance of D, right? And that should hold true for any given x and y. So for all xy, profile pxy should imply that x is of type D, right? And how we can do the similar thing for the range, right? So basically we are having the same thing. So if you have something like profile xy, then type of y is basically R, right? We are defining range here, right? And there are other axioms as well. So let us try to see what are those. So I'm asserting something which is always true, like what is the domain of range? What is the domain of range? For which you can define the range. So I can define the range of a property, right? A property, say P1, has got range to be, say, C1, right? A class. So the domain of range, so this is what we say, the domain of range. The domain of range is what? It would be property, right? So what would be the range of range? You see, what is the range of range? The range of range is a class, right? So the range of range is a class. What is the domain of domain? This is, and when we say something has a domain, of course a property has got a domain, right? So a property has domain to be the domain of a domain is a property, right? And what is the range of a domain? The range of a domain is again a class, right? So you see that we are using the first order logic, simply the first order logic, to represent everything that we know about RDF's vocabulary. We can define them, we can assert these axiomatic triples that we know to be true in RDFS. And as you have studied first order logic, we can easily relate first order logic with RDFS, right? So we are done with this particular part where we focused on how to relate the RDFS vocabulary with logic. There we have adopted two approaches to work on this relation. One is a set of deduction rules, and a first order logic way to represent the thing, right? Represent the constructs in RDFS. Now, let us look back at the deduction rules. What they are basically doing, they are basically helping out to provide answer to some queries from the knowledge base, right? And exactly that is what we are going to do in the next part of this module, the part 3 of the module, which is basically the SparkQuery language. So this is a query language that will be used to retrieve uh, mm, information from the knowledge base written in RDF form or with RDFS, right? And under the hood, all the things, all the deduction rules, etc., we have talked about, they will be coming to picture while a Sparkle query is put into the system to retrieve an answer. But in the next lecture, we'll be talking about basically the structure of the language and how we can use this language, this Sparkle language, to get information from the knowledge base. Thank you very much.